we're going today to speak about mostly the Gelfand transform, which will show us that any commutative sister algebra is of the form of continuous functions over a locally compact set. But let's start from discussing about we can start topologies for 1 minute. So the weak and weak star topologies. And let X be a Banach space. Then the weak topology on X, then weak topology on X is the weakest topology and generated by the continuous linear functionals. Over X.
עכשיו רואים בסדר.
אוקיי, כן, גם לי זה נראה בסדר מהקטע של עצמי, באמת. The weak star topology, so this was weak topology, weak star topology. The dual X star is the weakest topology on X star. Such that the phi goes to phi of X are continuous. In other words, a net of functionals phi alpha converges to phi if phi alpha of X converges to phi forever. And some theorems some of you are probably familiar with. Okay. Yes, Banach, blue. The closed unit ball of X star. And star is compact in the weak star topology. They say unit ball, I mean, of course, in the metric, it's the norm. Did you all see this once in your life?
I didn't.
What? You didn't. Okay, so it is. I'm not going to go over the proof, but it is something rather basic in function analysis, and you can open probably Wikipedia and read briefly. And also, another classical functional analysis theorem that we need today is the algebras theorem. Which says that if X is compact Hausdorff, and A is a sister algebra that sits in X, in C of X, such that sister subalgebra for simplification, such that it contains the identity, it separates points, and let's by this I mean I suppose that for every it's different than one X, there is F in A, such that F of X is not F of Y, and that it in fact then this has to be an inequality. So by the way, so this is a sister algebra, this is a sub-sister algebra, and there's a statement here about sister algebras, and something that you might ask yourself is there a generalization of this nice theorem for non-necessarily commutative sister algebras, right? This is commutative, so this must be commutative. So the question makes sense. Of course, there are no points anymore, but okay. But points are presentations maybe, and okay, we will speak about it maybe later, but I'm just said something.
Generalization in the sense that this may not be compact, or
that C of X may not be, well, maybe another sister algebra, not necessarily commutative. But
okay.
Let's talk about it maybe.
And just to make sure, sister subalgebra is closed in the topology, right?
Right. Which is normal.
Yeah.
And now, and just a small remark, I mean, okay, I wrote your C-star subalgebra. One of the ingredients of being C-star subalgebra is being closed under star. And is this theorem still true without it?
Yes.
Yes. So yes, I don't have here the proof of this theorem, but let's think about one of the examples which example I gave you, which was of yes, so one example I wrote last time was I think the disk algebra, right?
Mm-hmm.
Which is holomorphic functions on the closed disk that are continuous, holomorphic functions on the open disk that are continuous on the boundary of the circle. And this separates points of C of T. So maybe remark, and A of T, the disk algebra, and sits inside continuous functions on the circle. We mentioned this last time.
Mm-hmm.
It contains one. It separates points. But there is no, these are not equal. This is closed under star. This is So this is containing one CFT separate points. And satisfies every requirement we have from sisters of algebra. Except of being self-adjoint, meaning closed under star. Closed under star homomorphic function is not homomorphic anymore.
Maybe I'm wrong, but is it true even for Banach algebras?
No. So these are Banach algebras. So this is what I was trying to say. These are commutative Banach algebras. This sits inside COT. It separates points. It does everything it needs to do. It has all the structure. It's not only Banach algebra. It is even you can think of it as I can give it a star that will respect. Yes, that will respect this star. I can do it. So I can think of them as Banach star algebras even. But still, it will not be enough. Okay.
The only sub-algebra of A of B that respect star is the constant.
Yes, whenever you no, I mean you can do things like this, right? You can take the algebra generated by a function z plus z bar 1, right? This would be an algebra. Of course, it doesn't separate point, but this will be self-adjoint. This will be the system. I mean, of course, if you start with something that is self-adjoint and then you take everything it generates, you will get a system. Okay, so right. So this containing this, and clearly, yes, I didn't finish that. And obviously, but it's good. Strict containment. Okay. So let's start with Gelfand theory. We define theory. And let's say from now until the end of the day, unless I say otherwise, A will always be a unital, commutative, Banach algebra. And definition and multiplicative. Linear functional. Linear function is homomorphism of algebras. Homomorphism of algebras So I should have set up as an A. We're gonna have an A because I'm fixing variables. A. B. A. Of algebras from A to C. Let's go with this. And well, that is not zero. Okay, we will assume it is not zero. We will assume. We will assume. I mean, not assume. It's a part of the definition. It is not zero. Can define it otherwise. This is things are easier this way. Or equivalently, that phi of 1 is 1. So let's give it a name. Phi. So why did I say equivalently that phi of 1 is 1?
Phi of 1 squared equals phi of 1.
Phi of 1 squared phi of 1, which is phi of 1 squared because this is our homomorphism. So phi of 1 can be either 0 or 1. But if it is 0, then
Multiply everything by 1. And
then it is the 0 function, right?
Mhm.
So okay, I don't know why it's like this. But if 1 0, then phi of a is phi of a1 is phi of a times phi of 1. So phi. Okay. And theorem. So something is very unnatural here. What is unnatural? Okay. I defined something on commutative Banach algebras. And these Banach algebras, well, okay. There are algebras, of course, commutative, unital, fine. And this is some kind of character or a morphism to one of the simplest Banach algebras. I mean, so if we are in category that has more structure, and Banach algebra has more structure, they have some topologies, logical algebra. It will be natural if this definition will include something that has to do with the topology, with say continuity. I mean, if I give you this definition, you might ask yourself, didn't you forget to write here continuous homomorphism of algebras, right? Because there is more structure here. At least continuous, maybe more than that, maybe. I don't know. Something that has to do with the norm, but continuity. But so it would be a reasonable question to ask, but it is automatic. So and every multiplicative inner function is continuous, or bounded, if you want, continuous. With norm equal to 1. Let's show this. Okay, so so clearly, for invertible elements, phi of them cannot be 0, right? Because phi of the invertible element must be invertible. So for every A invertible, phi of A is not 0. And so if A is has no less than 1, then 1 minus A is invertible. This is something we saw last time. So phi of 1 minus A is non-zero, or phi of A is not 1. But now, I said that we're done more or less. So I want to say that phi of A needs to be less than 1 in absolute value, strictly less than 1. How come? Because, well, I wrote here that, well, I did this for the norm of A. So this line will remain true if I will multiply A by some lambda in the closed unit disk, right? So thus, for every lambda with the absolute value less than 1, repeat this process but with lambda A instead of A, and you will see that phi of lambda A is not 1. But this is already this is a disk, right? Oh, what do I mean by saying that this is this? So here's the picture. We have here these numbers phi of lambda A such that lambda is less than 1 equal. This is a claim, is nothing but writing phi of A absolute value times the closed unit disk. But we've just said that 1 is not in here. So we have this picture, right? The complex plane. We have here this thing, which has right with phi of A. And here we have the number 1. But this tells us exactly what I wanted to say. Phi of A is less than 1. So we started with an A with a norm less than 1. We show that phi of A is less than 1. And we're done. So phi is bounded with norm. Well, less than 1, but phi of 1 is 1, so yeah, equal to 1. Questions?
I have a question regarding the proof, like it was clear, but I have a general question because simply we assume everything is commutative, and I just missed the part why continuous functional commutative reconstruction.
Well, so last time we gave it as one of the first examples, system algebra or even Banach algebra, and the product f times g of two continuous functions. So what is the function f times g of x?
You take product, not like you don't define like it's the log of that.
No, it's not Arkava. Okay, sorry, maybe I should have said it. No, it's not Arkava. When I write c of x, I mean functions that are c value, that are from, so this is functions from x to complex numbers that are continuous. So you cannot compose them.
Okay.
The only thing you can do is multiply them. I think we discussed about this last time. Okay. No, maybe I maybe went too briefly over that, but so apologize. Okay.
In this proof, what is the case that A has a norm of exactly 1, but not smaller than 1?
What again? Say it again.
What with the case that A have a norm 1?
So it also has to be norm greater than 1. I'm just saying, we show that for every, if you show that for every element with a norm less than 1, you got something that has norm less than 1, then in fact you show this thing, right? Okay, I can put here another arrow. So for every A in a phi of A over 2 norm of A. Right? This is of a norm half.
Yeah.
0. No. So A is 0. So this is less than. Sorry. Okay, I need to take something very close to 1. So sorry. So take here some something.
1 minus epsilon, maybe?
1 plus n. Yes, this is right. Okay. So this is with norm less than 1. This is less than 1. Meaning phi of A is less than 1 plus 1 over n of A. Meaning phi of A is less than or equal to 1. And this shows okay. So yes, I skipped this somehow, but this is something you can always do. So yeah, this is very nice, right? Because we use the fact that we know that elements of norm less than 1 minus them is invertible. And then okay. So okay. By the way, question: if I have a commutative unital Banach algebra that happens to be somehow a division ring, so that does it have to be does it have to be a field? Does it have to be in complex numbers? So maybe just as a comment, so what do you think? So if I have a unital commutative Banach algebra that happens to be a division ring, so every element has a
What's the question?
do I know that
It is a field.
it is a field of complex numbers?
That
Can I be
field.
What?
If it's that field of complex.
That field of complex. So let's see. So note, well, I don't know, so it's quite a remark. If A is a unitary function that happens to be a division ring, then if A is in A and lambda is in the spectrum of A, then A minus lambda minus A. So when I write lambda minus A, I mean lambda 1. Okay. The lambda minus A is non-invertible. But this is a division ring. So if something is non-invertible, it has to be 0. It can't be the quaternion anything like this. Okay. So this is just one remark.
So it means that the only out of the algebra that it happened to be division ring is the complex numbers.
Exactly. And now a theorem. So this brings us to, in general, if you have a commutative algebra, you have the notion of ideals and of maximal ideals, and a Banach algebra, an algebra, a commutative unitary algebra over a maximal ideal. I mean, when you take a quotient by a maximal ideal, this is isomorphic to the field of complex numbers. I want to discuss a little bit about the ideas of unitary commutative Banach algebras, but before that, I want to emphasize something. So, theorem: if A is a unitary commutative Banach algebra, he said in the beginning that A will always be right in the commutative Banach algebra, but then started writing this again. I don't know why. If A is a unitary commutative Banach algebra, then any maximal, when I say maximal, I mean algebraic, of course. Algebraic ideal is closed.
Can I ask a question really,
About yes.
But somehow you have an assumption on the spectrum that is not empty.
Yes, so it's not an assumption. We mentioned this last time that the spectrum of any element in a commutative is by unitary Banach algebra is not empty, and in fact it is formed. Okay, this is for fun. Well-known spectrum functional analysis. Spectrums. Another question?
So just remind us what you mean when you say that the ideal is closed.
Closed in norm. So the ideal is a subset,
Okay.
right? That is defined from multiplication from right and left. And I can discuss about closed ideals, meaning that they are closed in norm.
The closed set.
Closed subset in topology. And the thing is that, well, why did I mention algebraic? Because, well, I think I said last time that when I said an ideal of a sister algebra, when I already know that I'm in the category of sister algebra, and I will say later an ideal, usually I will mean closed ideal automatically, because these are the right ideals in this category. You might say that, you might imagine that also the right ideal in this category of commutative Banach algebra needs to be closed, but I did not mention this, so therefore I verify this even if I didn't speaking about algebraic, and they said they are closed. Before that, maybe let me put this short lemma. If J is an algebraic proper ideal, of A,
Proper in the sense that it's not A.
proper in the sense that it's not A, then J closure is also such. Also such an ideal, it is proper. Well, why is this true? I mean, the fact that J closure is an ideal is very easy. Okay, it's clear that J closure is an ideal. The only question is why is it proper if J is proper? Why it happened? I mean, right? We start with J. J is algebraic ideal, so it has to be maybe even a dense set. I don't know, right? You can imagine a dense set that is still somehow happens to be an ideal, and then when you close it, you get everything. So why not? Why it can't be dense?
Because of the identity.
So what?
The identity has an open ball around it. And the closed ball, so whatever you want.
So
Of invertible elements.
Okay. So that's the point. The point is that invertible, so you can speak about identity, but even more than that, GL of A, the invertible elements of A, is an open set. So if they intersect J closure, they must intersect J, because it's a, but if J has an invertible element inside of it, then it's everything, so but it's not. So okay, so let me write it. But still is an ideal, so we must show it's proper. But if GL of A is open, so the fact that it does not intersect J, because J is open, implies it does not intersect J closure.
You say here, okay, you say if J is an ideal, then obviously J bar is also an ideal. Doesn't this already say that the theorem we want to prove?
The proper part is
No, but we want to prove that if you have an ideal, a maximal ideal, its closure, it's a larger ideal. But by maximality, it has to be.
No, but you need to know it's proper. That's the point. Somehow.
So the point here, okay. The point here is about the point here is the property.
The properness, right? Somehow maybe you can imagine that you have like an ideal which is dense. Somehow it's dense in your set, and then you can enlarge it and never get everything. And no, I mean, and its closure will be everything. So it won't be maximal. I mean, it's
Yeah,
Okay.
okay, I see. Because maximal by definition is, okay, I see. Maximal by definition means proper. Right?
maximal by definition
Yeah,
is
yeah, of
proper.
course it does, yeah.
Of course it does, right? Otherwise. So maximal by definition is proper.
So this is why you needed this lemma. The lemma is all you need.
Exactly. It's a proof of theorem. If J is maximal, interdimension. J is in J closure, which is strictly A, maximality. Is J. The only problem that we had here was the fact that maybe when you close it, you get everything. But it's not the case.
Why the set of invertible elements is open?
This is something we mentioned last time.
Oh.
So it comes from the fact that well, whenever you have an element in no less than 1, then 1 minus this element is invertible. Then we manipulated this thing to show that you can insert a ball around every invertible element made of invertible elements.
And did you use commutativity?
No.
No. Okay, so you just because it's true in general. Like,
Yeah. Yes. Yes.
I'm trying to follow the logic of this.
So the logic is like this. You need to show two things in order to show this lemma. One is just that J. I said J closer is also such. By such I mean two things: that it is an ideal and that it is proper. Namely, it's not all of it. It's an ideal easy. The exercise and nothing. The fact that it is proper, you can read it reversely. If GLA intersects J closure, because this is an open set, it intersects J. Right?
If it has an invertible element,
but then J will be everything because it has an invertible element and it's an ideal. But I wrote it.
And how do you know that J does not intersect?
If it intersects GLA, then J contains an invertible element. So it contains everything because multiply it by the inverse of this invertible element, and
Yes.
one will be there, and then everything is there. Right? Okay. So now we can there's also something small that is maybe trivial, but you mentioned this. Well, it's not trivial, it's need to use Zorn's lemma or equivalent, but every ideal, well, every proper ideal, algebraic ideal, contains in a maximal one, of let's say Zorn's lemma. I will not read the details, but you can think about it for 2 minutes in your hand.
When you say algebraic ideal, you just mean the regular ideal that we know.
Yes, that it is invariant to multiplication from left and from
Multiplication
left,
from left, from right.
both from left and right, from two-sided. Okay. And another remark I wanted to make. Maybe let me write remark 1 and then remark 2. Remark 1. Note that for every A in A. Sorry, not A in A that is not invertible. A in GLA, A that is not in GLA. I can always consider this thing, AA. Okay, which is all the BA such as B2. And here I'm going to use commutativity. Due to commutativity, this is a two-sided ideal. Hence, it is contained in a maximal ideal. And it is proper. So contained in a maximal ideal. So for this is a proper two-sided ideal. But I never like two-sided ideal. Hence, what we mentioned is contained in a maximal ideal. So, in a maximal ideal. So this shows that this shows that A is non-invertible if and only if A is contained in some maximal ideal. The other direction is immediate, right? Is it too small? Sorry for that. Maybe they don't know we're back and we're doing something.
Maybe a little bit larger.
Oh, okay, I'll try to. So, if and only if A is in a maximal. And remark 2, if phi is a multiplicative linear functional, then its kernel is clearly a maximal ideal. So it's more than that. It's algebraically it is maximal ideal. Well, it's not more than that. That's same thing. But I mean, it's algebraically maximal ideal because we know that A modulo the kernel is C. Right. So this is something from algebra. And conversely, if J is an ideal, which is if J is a maximal ideal, is the maximal ideal of A, then phi, or maybe let me call it phi sub J, which is the quotient map. So as I said, from just because this is a maximal ideal in the sense of algebras, not because there is some kind of a closure over it. So this is isomorphic to the complex numbers. So then this one is a multiplicative linear functional, and J is scalar. Thus, multiplicative linear functionals and maximal ideals are in one-to-one correspondence. Thus, multiplicative linear functionals are in one-to-one correspondence with maximal ideals.
This multiplicative linear functionals are functional To complex numbers?
Yes. This is what we said in the beginning of the last numbers. We define them as homomorphisms.
Yes, so just need to remember if it's
No.
complex numbers.
Sure. Okay. So corollary from these two remarks, from both remarks. A is non-invertible if and only if phi of A is 0 for some multiplicative inner function of F. Phi, phi, heaven. So this takes us to the Gelfand transform definition. The Gelfand transform we denote it usually by a hat which sits inside the dual of A. A is the set of all duplicative inner functions. And of course, we're going to equip it with some topology. Which one?
Star.
With star, why?
Was it in this?
Because we love, no, of course, but A star has its own topology, like it comes with topology. Right? But its weak star topology, what?
One question logic.
No, I mean, the topology of A star is a dual space. It's also a Banach space with it. But no, I mean, with a weak star topology, the unit ball which contains only multiplicative inner functionals will be compact, which is very useful thing to have. Not only useful, we'll see later that it's more than that. But for now, claim A part is closed in the weak star topology. Well, if phi alpha converges with star to phi, and these are all in A bar, then phi alpha of 1 converges to phi of 1. So these are all 1. So alpha is also 1. And phi of AB, which is the limit of the phi alpha, which are all multiplicative. Multiplication in the complex numbers, something that is bicontinuous.
This is because the both functional are continuous, right? The step.
What again? Say it again.
The step was because the two functional were continuous. That you took the limit of product to product of limits at the end. Because the two functional are continuous. So
What function is continuous? The only thing I use is here I use the fact that phi alpha is multiplicative, and here I use the fact that you have two nets of complex numbers. So multiplying in the complex numbers, it's something that is continuous from both sides, so it's bicontinuous. This has to do with the complex numbers. Okay. So, corollary A is complex. A hat is complex. This is from Banach. And I'm not going to do it this way, but just to let you know, this whole discussion that I'm doing now and that I did before can be done also in the language of maximal ideals and not multiplicative linear functionals. We said that there is a one-to-one correspondence between the two. If you work with maximal ideals, you need to use the Zarinsky topology instead of the Weizmann topology, and things work the same. I mean, these are two parallel ways to the same result. Okay, so what is the Gelfand transform? It's a map denoted by hat, goes from A to. Now this is a bit stupid or tricky, but it doesn't go to A hat. It goes to continuous functions normally. Is the thing. The field. And A goes to the function A that maps phi, right? These are functions over multiplicative linear functionals. So it will map phi to what? To what complex number? The only thing it can do.
Is those A not also the Gelfand transform?
No.
Yes, I don't know why I have another title. I mean.
Isn't it called the Gelfand space?
What?
Isn't this called the Gelfand space or something like that?
The Gelfand space. Yes. Or the Gelfand transform of the space. Yes, but the Gelfand space or the Gelfand space. I don't know why I write. I'm sorry. Thank you for that. Sometimes it's the Gelfand space also. Sometimes the Gelfand transform of A. Of capital A. Yes, and that's the transform. I have no idea. In my notes, I wrote the spectrum. I don't know why I'm exactly. Transform.
What is the C of A?
Continuous functions over these compact transverse space.
Okay.
Okay? With multiplication that is point. Okay. A joint is bar. Norm is infinity. So,
Right?
yes.
The Hausdorff property comes from the fact that you can separate points.
Well, the A star is outload.
Okay.
Yeah, so if you take a subset that is out, subset of the outload space. Okay. So, why is this continuous, by the way? I mean, I said it is continuous functions over A hat. But it is still continuous, right? Because what is the topology on A hat? It is the weak star topology. Namely, if phi alpha converges to phi, then A hat of phi alpha, which is phi alpha of A, converges to phi of A, because that's the topology. So it is indeed a continuous function. And what is okay? So now here's a nice property. The image of this function. So this function goes from A to C. the complex numbers. But what is the image of this? So claim the image of A bar is exactly its spectrum. 25. If I take lambda in the image, then it means that
Not the image of capital. Oh,
no, I'm doing it for lowercase, for single. Okay, this is for every. So we take lambda in the image of A, so it means that there is a phi in A hat such that A hat of phi, which is phi of A, is lambda. So this happens if and only if there is phi in A hat such that phi of lambda minus A is 0. But by this, we said that this property happens exactly when lambda minus A is not invertible, right? That there exists a speak-divisional function that sees that lambda minus A is not invertible happens exactly when lambda minus A is not invertible. In other words, lambda is in spectrum. Okay. So this was by the corollary from both remarks that was written somewhere. Here. It's here. Okay. Good. So what is the norm? What is the norm of I mean, I'm done with the claim, but we know from this claim we see that we can also say we know exactly what is the norm of A hat. If its image is the spectrum of A, the image of this as a function, as a continuous function, is the spectrum of A. So the maximal absolute value of an element in the spectrum of A will be this thing, right? But this thing has a name. What? How? Spectral radius, rho of A. So this is rho of A by white inches. But this is less than or equal to the norm of A. So we already see that the Gelfand transform is contractive. And also note, I mean, to see that it is contractive, I don't really need this fact. I mean, by definition, this is just phi of A.
Each phi was
supremum over all phi, and then you can contract the phi. But here I said something more important, which is this one. It is equal to spectrum values. We're able to deduce this without this observation. Another observation is that. So this is just an observation in okay? But another observation is that, of course, what is AB bar? Not bar, hat, AB hat. So AB hat of phi is phi of AB, right? The definition, which is phi A phi B, which is A bar of phi, B bar of phi. Right? So A B bar is A bar B. So hat. So hat is the Gelfand transform is also multiplicative. So it is a contractive homomorphism, of course, it is a linear. Yes. So it is a contractive homomorphism of Banach algebras. So the Gelfand transform Gelfand transform is a contractive homomorphism of unital commutative Banach. Well, now let's go back to sister algebras. So we're now in a situation that we have something really nice, right? Whenever we have a unital commutative Banach algebra, we can find a contractive map into this sister algebra of continuous functions over this nice compact set, right? If this Banach algebra happens to be a sister algebra, then this is an isomorphism. So theorem, if A is the commutative, is the unital commutative, unital. Sister algebra. Or A is a commutative unital sister algebra if and only if the Gelfand transform is a star isomorphism. Then Gelfand transform is a star isomorphism. So what is a star isomorphism?
Isomorphism which preserves star.
It's an isomorphism of algebras with reverse star. And on the way, so we're going to speak next week a lot about star homomorphisms, I mean, errors in the sister algebras. But it's also going to be isometric. Okay? Yes.
Don't we use the fact that A is a sister algebra in this equality?
This one?
The equality above.
No, this is true for any Banach algebra. We mentioned this stuff.
No, but the part of the equality is
also for any Banach algebra. True for any Banach algebra. The fact that the spectral radius is less than or equal to 1.
And both injectivity and surjectivity can fail if it's not a sister algebra.
Let's see from the proof. Okay, so let's see what can fail exactly. So before the proof, just I want to make a quick lemma, but maybe let me start the proof and then make the lemma.
Can you just make what is it? A star isomorphism?
This A is of English like something, and the star isomorphism.
Okay.
Yes, and this, for the moment, it means isomorphism of algebras that preserves a star. And later on, I will take more. to prove so we need to show first that it preserves star, and then that it is isomorphism in the sense that it is injective and surjective, and then we're more or less done. Okay, but let me start from showing that it preserves star. So and of course there is this direction, which is clear. If it is, I mean, this is clear. If it is isomorphic to, this is a sister algebra. So if something is star isomorphic to sister algebra, it is sister algebra because yeah. So okay. So no, because it will preserve it will have the sister identity, right? Through the isomorphism. So these directions. So what will be this direction? So first, let's show it preserves star. And note that, so I want to say that to show that something preserves star, it is enough to show that it maps self-adjoint elements to self-adjoint elements. Okay, so let's do it like this. So a small claim in the proof. Claim. If A is self-adjoint, then the spectrum is real. And this is true in any, I'm not going to use the commutativity of the sister algebra, this is true in any sister algebra. So why is this true? So if you take an element in the spectrum, write it as alpha plus I beta, or alpha beta. And we want to show that beta is 0, right? Mm-hmm. To show that it is that the spectrum is real. So for I want to add lambda, some lambda to this beta. So for every lambda in R, alpha plus I beta plus lambda belongs to the spectrum of A plus I lambda, right? I just added I lambda to both sides. So this means, in particular, alpha plus I beta plus lambda is less than the spectral radius of this and also the norm of this, right? This is, now let's square this thing. And this thing is more or less, or exactly, alpha square plus beta square plus lambda square plus 2 beta lambda. Mm-hmm. right? Alpha, beta, and lambda are real. This thing, and this is due to the sister identity, is A plus I lambda star A plus I lambda. But A is self-adjoint. So A star is A. I lambda star is minus I lambda. So this thing is equal to A minus I lambda, A plus I lambda, which is A squared plus lambda squared. Which is less than or equal to A squared plus lambda squared. And we're done. You see why? Because now we got rid of the lambda square. We have here lambda square and here lambda square, so we can erase them both. And we see that something plus 2 beta lambda is less than or equal to something. But this is the only place where I have lambda. And I can take lambda to be any number, right? As large as I want, so then this will remain true. So somehow it means that beta has to be 0. So A squared plus B squared plus 2 beta lambda is less than A squared. So beta has to be 0. This was one. So this was just this claim. Back to the proof. So I said that I want to show that it deserves star, right? So if A is an element in a sister algebra, also I'm saying something that has to do nothing with the fact that it is commutative. By the way, also in this claim, I mean, if you're taking notes, please write that. This is true in any system. Tom will not be able to see it, so I'm going to left forever. This again has nothing to do with the fact that we're in the commutative case. And we will use it later, but that's the reason I'm stressing this. I mean, I believe basically. No, I'm sure we will. If A is an element in a sister algebra, then I can always write A as then we can decompose. We can decompose A as A equals to B plus IC, where B and C are self-adjoint. How come? How can I do it? So who are going? I'm going to give me a recipe. Who is B and who is C?
A plus A star.
Exactly. B is A plus A star over 2. And C is
A.
A minus A star over 2I, right? So you can check that these are both self-adjoint. And of course, if I take this linear combination of them, then I get A. But if A, okay, not that. I want to say, okay, this is one thing. Now, if A is self-adjoint, then by the claim, the spectrum of A is in R, but by the previous theorem, the spectrum of A is exactly the image of A bar, of A hat. The image of A hat is in R, meaning that the Gelfand transform preserves self-adjointness. But with this decomposition, it means that it will be self-adjoint. So if A is equal to A star, then by the previous level, namely, the Gelfand transform preserves self-adjointness. Thus, for general A, that is equal B plus A IC with B C self-adjoint, we have that phi of A star is phi of B plus IC star, which is not phi. Sorry. I mean, yes, but I want to do head, but I want to
head on phi.
On phi. So maybe let me write this over here. So that's for every phi in A hat, A star hat of phi is phi of A star, which is phi of B plus IC star, which is phi of B star is B, plus IC becomes minus I C star, which is, see again, this is phi B minus I phi C. But now these are real numbers by what I've just mentioned here.
Mm-hmm.
But these are real numbers. Real numbers. I mean phi B and phi C. So this is nothing but phi B star minus I phi C per pound, which is phi of B plus phi B plus I phi C bar, which is phi b plus IC. Wow. Which is a bar of phi. Okay,
So the
so
function on A hat, it's the multiplicative function, right? Multiplicative.
yes.
We always look at that.
What? Well, yes.
We don't look at all of it.
No, that's the Gelfand spectrum, and this is the. Okay. That's the correct sentence. Describes the place where these functions live on. And fine. Okay. So that it is a star. So it is a star morphism. Now, so the Gelfand transform is star morphism. The fact that it is multiplicative, I said before, right? So now I want to show that it is injective and surjective. So since A is commutative, and all of its elements are normal, right? Just by commutativity, all of its elements are normal. They commute with their star. So this answers also to Itamor's question. So for any A, the norm of A, which is rho of A,
This answers my question because this equality be proved only for C-star algebras, or
yes. Of course, no, it does not completely answer the question.
Yeah,
I need
but
to
it's
give for example. Anyway, so the Gelfand transform is isometric. C-star algebras, in particular, it is injective. Finally, surjectivity comes from well, let be the image of the Gelfand transform. So, right, I want to write something like this, but this is not a half. Here's functions over. Well, yes, well, it sits here, right? I didn't. The image of the function. Does it okay? Is it okay? The wrote it like this, and I mean that the B is just the image of the Gelfand transform. So we're done. So clearly, B separates points of A at and contains one by the Stern-Weierstrass theorem. It is everything.
in here we didn't use system.
Standard algebra is for C-star. We gave an example before. No, you weren't here. I remind the standard algebra, and somebody asked if the standard algebra is true for Banach algebras or anything like this. And we just give an example. So think about the disk algebra. It sits inside continuous functions over the those, the unit circle, right? The disk algebra is just all the homomorphic functions on the open disk that are continuous on the boundary. So it separates points. It contains the identity, but it's not closed under star. And I mean, it has.
So you only need so you don't need it to be a C-star. You need to be a star.
No, I don't need the C-star identity.
But you need the
no, star Banach algebra is not enough. I need more than that. Well, the thing is like this: you can make the Banach algebra of holomorphic functions to be a star subalgebra just by this kind of star. So f star of z.
Twice.
Yeah, something like this. So I think this is a. No, but this does not agree with the star of the continuous functions of the root those. So now I. I see your question.
I mean, some versions cannot assume that it's a system algebra because it's about density, not about something closed.
Yeah, no, but the thing is like this. No, it is a system. Sorry. The thing is like this. The big thing in the Stolvarch class, I mean, the big thing is by assumption, a system algebra. It is continuous functions over a couple out of set. And the small thing is a subalgebra of that. So in particular, it is a system subalgebra. Well, the only thing is the closeness, but it has everything, I mean, except of this, so it has the sister identity with the star that comes from the upper. So the small thing in the Stolvarch theorem, I mean, a priori, well, okay. So how do you formulate the Stolvarch class? I formulate it like this: if you have a closed system subalgebra, you can say a closed algebra that's closed under star, but it will be the same thing. You can say a closed star subalgebra of C of X that separates points from anyone, then it's everything. So it is a theorem about system algebras. I mean, you can't avoid it, right? If it's closed under star, it's closed and it's subalgebra, it is system subalgebra. And you can't. There isn't a way to generalize this somehow.
You don't have to require it to be closed, and then you can say it's just dense.
Oh no, not closed. You can say it's dense. It's the same thing. This is good. Okay. So this use the fact that it is system algebra.
Hey, we know that the image is closed. This we already know that the image of.
So we know that the image is the image of, yes, I will say that I didn't say that the image is closed. Let me think. I didn't say that the image is closed. You're saying. Let's think about it. So if
you said it's isometric, the map is isometric, so to prove it's injected, it's isometric, it's closed.
So what?
The image has to be closed because the map is isometric.
Why?
That's how you prove the injectivity.
Right. So you're saying that if I have a net if I have a net of
But if the image wasn't closed, that you can
exactly because of the isometry.
Yeah.
Good. Yeah, so I should yes, but you're right. For some reason when I wrote this, I thought it is immediate. It is immediate from isometricity, but maybe it's worth writing this too. So let me just add another line. So the fact that B is closed followed by the fact Guy transform awesome. And then we can enlarge class in the way I moved it. Okay. Right, so now we know that any commutative unital sister algebra is isomorphic as a sister algebra to the continuous functions over a compact Hausdorff space, not just a compact Hausdorff space. In fact, it is the set of all multiplicative linear functionals, or so we can think about it as the maximal ideal space. Sometimes people think about it as the maximal ideal space. Anyway, this is called the Gelfand spectrum of the algebra. We didn't mention the case when the algebra is non-unital. So what happens when the algebra is non-unital? Well, let me maybe briefly just comment that remark. If A is non-unital, then we can always consider its one-point unitization, right? Its one-point unitization would be unital, commutative sister algebra. Hence, it will be isomorphic to continuous functions over some compact Hausdorff space, where the Gelfand transform of the Gelfand spectrum of. Sorry, I denoted maybe by A plus, right? The unitization from last time. But then A sits in A plus as a maximal ideal. Okay, so I will leave it as an exercise. So this tells you, so A separates points, but does not contain points of X, but does not contain 1. Thus, from another version that you can easily prove of the Stern-Weierstrass theorem, it means that A is isomorphic to continuous functions over X minus 1 point, but this is not compact anymore, so I need to take here the vanishing this point.
Can you just repeat what do you call the Gelfand spectrum? What if
They say about this thing. The set of all multiplicative linear functions for some fixed.
You can think this point as the infinity.
Yes, exactly. You can think about it as an infinity. And
so you have, if I think topologically the process of adding the unit is like the 1-point compactification?
Exactly. So this is something we mentioned, I think, last time. So adding the unit corresponds to the 1-point to Alexandrov compactification. This is something we mentioned last time, but now we see it. Now we said something more general in some sense. So that anytime you start with a non-unital commutative sister algebra, it is of this form. So now we know any commutative algebra is of the form, any commutative sister algebra is of the form C of X. Any commutative unital sister algebra is of the form C of X. Any commutative non-unital sister algebra is of the form C0 of some locally compact household space.
The reason that this X0 that you take out isn't like a discrete point, isn't like
the reason it's not a
because then
discrete,
it would still be unital, right?
right? Exactly. Yeah. Exactly. So in this remark, there are some things to verify. Let me leave it at this point as an exercise. Verify the details. Verify the details. Exactly. So in fact, by the way, let me mention another thing. So in this case, you can think of, that's funny. So A is continuous, A plus the 1-point integration is continuous functions over X. A without the plus, which is an ideal in A plus, is continuous functions over X minus 1 point. Now let's think about the quotient, right? We have an ideal inside the sister algebra. The quotient, which is isomorphic to the complex numbers, you can also think about it as continuous functions over this 1 point, right?
Which is just C.
Which is just C. Yes, we knew it will be C. I mean, it's another way to think about it. And this is something I want to general for a second. I mean, okay, also as an exercise, maybe. Show, in general, show that whenever, well, maybe show that for every subset F inside X is compact outflow, and F is closed. All the functions in C of X that vanish on F is an ideal. Okay, this is, I mean, there's nothing to show here. It's an ideal of C of X. Here there's nothing to show, I mean, it's immediate. Of course, the multiply function in JF with another function, it would be still in JF. So that's immediate. I'll show that. And show that every ideal of C of X is of this form. Now by ideal I mean closed ideal. Okay, because we are again back to C star. So ideals are closed. So if I start with the closed ideal of C of X, then automatically I can find an F such that J is JF. Okay, and you can also think of and A modulo JF. You can think of it as continuous functions over F. Okay, so now you see that somehow that there is very rigid correspondence between topological, compact Hausdorff spaces to C-star algebras, and how encodes the subsets. The subsets are encoded as ideals, and vice versa. Ideals are encoded as subsets in terms of. So we have some kind of duality between two categories: the category of C-star algebra, unital commutative C-star algebras, and the category of thousands. Which is, well, and we could translate more or less everything. Okay. So now, how are you, by the way? Are you okay? Can I continue? I know that we took the break a long time ago, but.
Can you add to this?
Yes. Thank you.
I just want to ask, like, the Weizmann proof that we did was to show before that all the continuous functions defined on all the continuous functions defined on a star algebra can be written in this form.
Again, all
you've written a form you've written a form, right? You said that B is equal to C.
This thing?
Yeah, this was B, and that was the function that you defined, right? When you said C,
this was just another way of writing all the A hat A in A. Okay, and I just want to say that that's everything. This is what we showed when we wanted to show
all the continuous function.
All the continuous function, yes.
And then, but you also give an explicit form of B.
That's explicit. Oh, maybe I missing the point.
No, you said, but didn't you say that B is like a function in B? It takes something like this and give five.
I said what is a hat? A hat of something in here, multiplicative in a functional, is 5A.
Mm-hmm.
Okay. Yes. So that this was the question.
Yes, and that's but you say that's all the continuous function.
Exactly. That was the surjective part of the last theorem. The last theorem told us that we have an isomorphism of C-star algebras between any unital commutative C-star algebra and its continuous functions over its Gelfand spectrum and the image of the okay. So this means that if you start with the unital commutative C-star algebra, you define these continuous functions over the set of multiplicative linear functions, and you get everything. So yes, and by the way, so can you name this missing point here? What do you mean by what do I mean by name it? So I mean this X is the Gelfand spectrum of A class.
Mm-hmm.
So it means that there is a special multiplicative linear functional that I'm going to throw away
constant one.
The constant one, why? I mean, so the first why it's not linear, right? The constant function one is not linear, right?
It's at the image of one, the unit. No.
Yeah, okay, yes, well, okay. So
Maybe zero, the constant zero, like the function of zero, which is not, we didn't call it.
exactly. So when we define multiplicative linear function as before, right? We gave a definition, and then I said, but I don't call zero, I don't call it a multiplicative linear function. If I would call it a multiplicative linear function, then in the usual theorem at the end, I will need to erase it, right? Somehow. So, but what happens when you take the unitization? So you have this zero map that takes everything to zero. It's linear, it's multiplicative, it's a multiplicative linear functional. It does not take 1 to 1, but suddenly when you consider it, when you extend it to the 1 point unitization, then the extension goes, well, it exactly takes 1 to 1. So suddenly it becomes a multiplicative linear function, right? In the sense that it's the non-zero one. So it appears in A plus, but you don't see it in A. So this is exactly what you need to remove. That's the multiplicative linear function you need to remove. So this is something that if you do this exercise, I mean, I hope you will verify. This is the one, this row. Okay. So there is at least one thing that I want to do today, which is, well, you can think of it as an example, but it's a bit more than that. And okay. So example.
If A was a priori uniform,
Yes.
then A hat would include the zero functional?
No. We said that multiplicative linear functionals are not the zero ones. They are multiplicative, they are linear functionals, and they are non-zero. Okay, so we remove them. But somehow they needed to be there. You will not see them, but where do you see them? You see them if you started with something that is non-unital, and then you raised it up to something unital, and then suddenly it is non-zero. So see. So, okay, you can think about it. Okay. For example, and let me say that it is, for now, it will be an annoying example. So I will explain why it's going to be annoying. Let A be any sister algebra. Well, let's take it unital for now. I can do it also without unit, right? Be any unital sister algebra. And A, in A, normal. Right, so A commutes with Consider the sister algebra generated by 1 and A. So what is the sister algebra generated by 1 and A? No, it's more than that. You need a star sister algebra. So you can think about it in two ways. One way,
Polynomials.
take polynomials in 1, A star, and multiply them and you need to close it. So I don't like to define things like this, but it's true. It's easier to define it like this. Take all the sister subalgebras of A containing 1 and A and intersect. So it's the smallest sister algebra subalgebra of 1 and A. So consider that, let's call it smallest. sisters of algebra. Of A containing A and think about it. It has to be commutative because A commutes with its star, it commutes with 1. And of course, it is the closure of all polynomials in A and A star and 1, as we described before. But okay, so obviously, the C star of 1 of A is commutative. And unitary. So it is isomorphic to the continuous functions over some compact outer space. What is this compact outer space?
So did you just say it's the multiplier?
It's the multiplicative linear functionals over the system. Right. So this is just to phrase the question. What is this? I mean, can you identify this in an easier way somehow? So yes. So yes, what's the spectrum? Right. So it's the same. So how did you see it?
Because if you take A minus lambda, so you get like an ideal, which is maximal, and then.
Oh. Okay. Now the annoying part. So this is a new sister algebra. Call it for a second B, right? This is a new sister algebra. This is the old sister algebra A. What I'm going to claim is that X is homomorphic to the spectrum of A inside B. So what's the relation between the spectrum of A inside B and inside A? Of course, one of them is inside the other, right? If you are invertible in B, if you're invertible in something small, then you're surely invertible in something big. So if you're not invertible in something big, you're not invertible in something small. So if you're in the spectrum, so these always contain the spectrum of A. And inside it's always in the system. And this seems like some weird technicality. I mean, the fact that it has to do with the sister algebra that A generates. But okay, we will discuss about this next week maybe. But for now, let's show this. So, proof.
Can you give an example of strict inclusion in this case? Because
yes and no. No in sister algebra, but this is a square for next time. Yes and no. So proof, well, we know that X is indeed the Gelfand spectrum. This is the algebra, which is all multiplicative functionals over system of 1A. Since, as we said before, polynomials in 1A, A star are dense in, this is just the Bachelor's theorem again, if find psi and multiplicative functionals and phi is equal to psi, then sorry, and phi of A is equal to psi of A, then phi is equal to psi. Thus, this map is 1-to-1. And it is also continuous definition by definition. Of the star topology. Its range, we know its range, before. Its range is the spectrum and is its image. Is the spectrum A. But again, side B. So am I done? I have a 1-to-1 onto map. Right? So A hat from so C star 1A to spectrum B of A is 1-to-1 and onto and continuous. Is it enough to say it's homomorphism? In general, no, but since we're speaking about compact spaces, that this is true. In general, in the category of topological spaces, being 1-to-1 onto and continuous does not imply that you have an inverse that is continuous. Probably in your life you had one example of this at a certain point, but if you come from a compact space, then this is true. And which is homomorphism. Since and the objects are compact. So we didn't do this exercise, but in case you, okay, we're done with the claim. Another exercise. If f from x to y, both compact Hausdorff, is well, I call it exercise. Yes, we're going to do something that is more general later on, but right now I can just say that if you have a map that is homomorphism, then the composition that we have, then this map, F star, which maps G into the function G composed with F. So f takes x to y, and then g knows what to do to y. Makes sense? Then this one is the size of the field. Corollary. C of system of 1A is nothing but the continuous functions of the spectrum of A. The annoying part is this B. Somehow, I mean, that makes sense in some sense because we give inside some sister algebra, but
This is exactly system of one.
yes, this is. I think it would be better if somehow this would not have depended on the place where I live. And spoiler for next week, it's not. It's equal to the spectrum of A inside any other system. Questions?
Question, but you saw that there is a homomorphism between the spectrum of A and B to the multiplicative linear functional in this system algebra.
I saw that there is a morphism between what to what?
Like between the spectrum of A inside the spectrum of A to this system to this multiplicative linear.
I saw the reverse direction from you to you.
No, yes, I mean, you said that this is a homomorphism, right?
Yeah, so there is an.
But this is just the functionals themselves. It's not a continuous function of the function.
These are multiplicative linear functionals
Themselves. And before that, we talked about the continuous function.
Multiplicative linear functionals are automatic continuous. I think well, this is continuous functions over a compact Hausdorff space.
Okay. Yes, and this is
And this you should think as the compact Hausdorff space.
yes.
That's your X.
Yes.
Okay, so see you next week.
Thank you.